Hello and welcome to this tutorial about complex numbers. In particular, we would like to talk about concept of phasors and how we can convert the Cartesian complex number to the concept of phasors. What you see in this slide right here is Cartesian or rectangular format for a complex number, where we have this complex number v equals to a plus jb. Now, j is the unit for the imaginary number, where j squared is equals to -1. And we can show this Cartesian number in this diagram. As you can see, the x component coefficient is a, and the y component in the imaginary part is just b. So we can show the same number with a vector, as you can see this vector here. And this vector obviously has a magnitude and also has an angle. And essentially showing the complex number as a vector with its magnitude and angle is known the polar format or the phasor format. And it comes from the fact that we can show this complex number also as exponential complex number, as you can see here. Now we can convert rectangular format to the phasor and vice versa. In the next slide, we would like to talk about this conversion. For the case of converting the Cartesian or rectangular format to phasor, the magnitude of the vector v is a square root of a square plus b square, where let's remember that a is the real part and b is the coefficient for the imaginary part j. Also, the angle theta, as you can see, theta here is the inverse tangent of b divided by a, where again b is the coefficient for the imaginary part and a is the real part. We have a numerical example here where we have this rectangular image complex number of 3 plus 4j, and first we use the Pythagoras theorem to obtain the magnitude as a square root of 3 square plus 4 square, which reduced to 5. And also the angle of theta is tangent inverse of 4 divided by 3, which is 53.13 degrees. And when we talk about the tangent, it's about this rectangle, 4 divided by 3. So based on these two values, the phasor format is very easy to be shown with the magnitude of 5 and then the angle of 53. Let's take a look at another example that we have here. And in this example, essentially the complex number is -6 minus 8j. And that is -6 and -8j, and this is the vector. The magnitude is straightforward. Real part square, imaginary part square, a square root of that, which is going to be 10, where this value of this magnitude of this vector is 10. But what about the angle? When we type the angle, tangent inverse of 8 divided by 6, sorry, that reduced to 53 degrees. But then that theta is this angle right here. Maybe I use a different color to make it more clear. So this is theta. But the actual angle, you need to add another 180 degrees because this vector is in the third quadrant. Okay, so then the actual result would be 233.13. And this is something to be aware when you're using your calculator. Make sure it provides the right angle. Otherwise, you got to visually inspect and make sure this is the right thing. Anyway, based on what we just discussed, the magnitude is 10 and then the angle is 200 from here all the way to here is 233. Okay. Okay, let's take a look at the next example. The next topic. The next topic is also very useful, the relation between the phasor and complex exponential. Uh, in the next video, I would like to talk about the concept of phasor and how we use that in circuit analysis, in particular in analysis of AC inputs. And let us assume that our AC input, in particular voltage, is defined as V equals to V of M, where V of M is the magnitude, times cosine of omega t plus phi. Okay, we can convert this this time domain function into a complex expression using the Euler formula. When in the next presentation I talk about phasor, you would see it's very, in fact, beneficial to convert the time domain function cosine of omega t plus phi to the exponential, to the complex exponential part, and use the concept of phasor. It's going to simplify analysis of AC circuit by avoiding differential equation, and let us just use algebraic equation. So be aware that the other presentation is coming up soon. Okay, so the idea is that I want to use the Euler equation, as you can see it here, now to write down or rewrite the equation for the voltage. Now, let us assume that this real part cosine of omega t plus phi can be defined as real part of this complex exponential, and that comes from, can be validated just checking the Euler equation. Now, if we define the phasor, okay, V tilde as the phasor, as V of M times e to the j phi, where V of M is the magnitude and e to the j phi is the angle, then all of a sudden the V of t at the very top can be defined as real part of the phasor, okay, V tilde time e to the power of j omega t. I mean, it's going to be straightforward to show that. I write it down here. Well, this can be expanded as real part of V of M e to the power of j phi times e to the power of j omega t. And then you can add the powers together and type it as real part of V of M e to the power of j omega t plus phi. And that's going to be equal to real part of V of M cosine of omega t plus phi plus j sine of omega t plus phi, where obviously the real part is just V of M cosine of omega t plus phi, where this is exactly what we define our time domain function. Okay, so the key relationship takeaway is that if we define our time domain function as V of M cosine of omega t plus phi, then the phasor for this equation is V tilde equals to the magnitude of V of M and the angle of phi. Once again, you would see that why this definition for the phasor going to simplify a lot of calculation when we are analyzing the AC circuits. Okay. Next slide is just a reminder that how we can multiply or divide two phasors, and it's going to be handy because it simplifies multiplication and division of complex number. Okay, let us say that our first phasor A tilde has the magnitude of A and the angle of theta A, and the second phasor has a magnitude of beta and angle of theta B. Then if you want to multiply these two phasors, simply the magnitude is multiplication of A and B, and the angle is just summation of the angles, theta A plus theta B. And for the division, you just divide the magnitudes and subtract the angles, theta A minus theta B. Here is a numerical example. Well, the first phasor has a magnitude of 4, angle of 30, and then the second one, magnitude of 2, angle of 45. Now, A times B is just 4 times 2, and the angle would be 30 plus 45, so the result is another phasor with the angle of 75 and magnitude of 8. And in case of division, it's just you divide 4 by 2, and then you subtract 30 from 45, which you get minus 15. Obviously, if you convert these phasors to rectangular format, you can multiply or divide these complex numbers as you guys are familiar how to. Well, as we mentioned before, phasors simplify multiplication and division. However, if we want to do addition or subtraction, it's much easier to first convert the phasors to rectangular format and then perform addition or subtraction. And here is like the equation how we convert a phasor to its rectangular format. And essentially we are using the Euler formula because, for instance, if I'm talking about A, this complex number A can be defined as A e to the power of theta A j. Okay, and then using the Euler equation, I can write it down. It's equals to A times cosine of theta A plus J sine of theta A. And that's exactly what we have here. Okay, and similarly, we can write the rectangular format for the phasor B, and then once we have the rectangular format, it's very easy to add or subtract them. And if this is the result of that, we can again convert that to magnitude and angle so that we have it in the phasor format if needed. I guess the last slide that I have here for you guys is just one example that I have two phasors and I convert them using the Euler equation to the rectangular format. And let us just take a look at this. For instance, the first one is 5 and 30. So you have the magnitude 5 here, and then the angle would be cosine of theta plus j sine of 30, which reduced to 4.33 plus 2.5j. Similarly, phasor B would be defined as 5.66 minus 5.66j. And then we can add these two phasors and obtain the value of 9.99 minus 3.16j, where we can convert that into a phasor again by obtaining the magnitude as 4.99 square plus 3.16 square, which is going to be 10.48, and then the angle would be 3.16 divided by 9.99, where in this case would be minus 17.5, or this is going to be your phasor. Okay, thank you so much for your attention, and please stay updated because I'm gonna upload another video where we talk about the concept of phasor, but more about its application in analyzing AC circuits. Thank you so much.